Hello, folks. Hope you guys are doing okay today. I'm gonna check, make sure everyone's here. Okay, it's telling me that my connection is not good, so I'm going to shut the camera off, save a little bandwidth. Anyway, can anyone not hear me? You can raise your hand or. Okay, I'm going to assume you can. So, first off, anyone got anything they want to say before we get going? I know that some of you have a lot going on in your lives now, so. Okay, anybody got a question about the class or anything like that? Or a comment? Have you heard about what happened in California? Think of, you want to share what it was, Gary? Oh yeah, of course they did, because they're crazy. Sorry about my phone ringing. I didn't have the ringer off. 1,000 people. Oh yeah, same thing in Florida. Yeah, yep. And I saw a news clip where there was a large party in Chicago where there was a lot of people came to the party. And I think part of that is because early on we were getting this story that it's not going to affect younger people, so therefore, have fun, get out. I don't know. It may have been Southside. I don't know where the party was. And, okay, there we go. Erica got the word. But anyway, I think because the word went out early that, if you were, 30 or younger, you had nothing to worry about. You could just go on like nothing's happening. And then recently we've had some folks that had mild case of the corona, and then all of a sudden they have a stroke. And the physician that's trying to treat them can't really do much because they're like having blood clots all over the place, and it's something to do with their immune system, I suppose. And there's a lot that we don't know about this whole thing, and we anyway, you guys know you want to be careful and do the best you can. I know some of you. How about pneumonia? Yeah, of course. Pneumonia, latches on. It's an opportunistic bacterial infection. So anytime you have something that is keeping your immune system occupied, then pneumonia can latch onto that. That is with people that have compromised. I get it out in a minute. Compromised immune systems, or they're older or whatever. But anybody can get pneumonia too. So yeah. So anyway, what we got here? May. Oh yeah, I'm sorry, May. I had a message that said, yeah, a message on my screen popped up said my connection's not good. So let's see. I've shut off my camera. That's about that will help my. Who knows? It may not even be my local connection. It might be Blackboard's doing it. Gary, can coronavirus? Well, pneumonia term is referring to a bacterial infection. It's the pneumococcus bacteria. Um, and I'm not, you know, I'm not a microbiology guy. But anyway, but the symptoms are the same kind of thing. You start out with upper respiratory, and then if it moves down into the lungs, that's when you're really in trouble. Is when it moves into the lungs, and that's where people wind up on respirators and all that kind of stuff. So, or ventilators, I mean. Um, okay, let me try something here. Is anyone still having a problem hearing me? Okay, I'm going to assume that cleared up. If you guys notice you're having trouble hearing me or something, let me know, or having trouble seeing slides or something. I can always go through my cell phone to get a different connection than going through my Wi-Fi. And that may or may not actually accomplish anything, but I can always try that. So I want to go to, unless there's another question. Okay, whoops, is it doing it? Yeah, it's doing it. Okay, so starting out here at the top, we've had some people having sapling login issues. Not everybody, just maybe a person there, and I don't know what's going on with that. So I've had one email back and forth with sapling, and they sort of talked about some stuff, but I don't think, anyway, I don't know. So anyway, the main thing is I sent this announcement out. Recently, I've had a few students with an issue of sampling assignments, getting into those. Oh, let me read your note, May. I didn't. It popped on through pretty quick. I've had issues with Blackboard in general. Maybe it goes on. I don't know. It could be Blackboard. I don't know. And Sapling was trying to hang it on Blackboard, which is a typical tech answer, is to blame the other technology. And a lot of times that's not the truth. They are lying. But anyway, we'll get it worked out. So main thing is, if you're having trouble getting into Sapling, you need to email as soon as you notice it and tell me as much as you can about it. Include in your message, of course, what class you're in, because I can't remember everybody, sometimes. And also include in your message what browser you're using when you're trying to access it. Okay. Okay. Well, let me know in an email you were having trouble getting into Sapling, what browser you were using, because they're also Sapling starting to blame that people are using the wrong browser. But so I've said to them, what browser should you use with a PC? What browser should you use with a Mac? And previously they were saying it should be Firefox or Chrome. And I've always used Chrome and not had any trouble from my viewpoint. So, but anyway, let me know as soon as it happens, and I will send that out to them, because this is no time for Sapling to be having problems. We're just about done with the semester. So I just need to know if you're having an issue with that. Okay. I don't think there's anything else here to talk about. But speaking of Sapling, these are all the assignments now through the end of the semester. So because of some login issues, I have got Chapter 6 moved to April 29th. And if we have any further issues, I'll move it more, and hopefully we will not run out of semester to move things to. But you do want to be doing chapter 6 for sure. Since we're now into chapter 7, you need to finish up on 6, assuming you can log in. And you need to do this one, practice drawing molecules. It's not for credit, but it's how you draw molecules using sapling. And then we've started into chapter 7, so you could start trying to do some of this, although we haven't done enough of it for you to really be comfortable doing chapter 7 probably. And then following 7 or 8 is a very, very, very short chapter. It's really just one idea. And then we have the gas chapter coming up at the end. So anyhow, that sapling, just if you're having trouble logging in, please let me know. And even if you gave me a like Umu, you said you had issue, just send me an email too, please, so I won't forget you, and then I will pass your information on to sapling, because everyone that's had an issue, I have sent them their name so they can go and check on that person's access. So okay, I think that is it. So I'm going to close this off. So now, does anyone have a question or comment? We'll try turning my camera back on. There we go. Anyhow, so anybody, question, comment, anything? Okay, so we're going to go back into the molecular geometry chapter. So I'm going to put that up, chemical bonding and molecular geometry. And I need to make sure that we are on the right slide. Okay, looks like we stopped at slide 10. So these are the steps that we're going to use for drawing Lewis structures, and we'll just keep going back to these every time. But you progress through these in order. So your first thing is you have to figure out how many valence electrons you have, and then if it is a polyatomic ion, you need to add an electron for each negative charge that it has, or if it's a cation, subtract 1 electron for every positive charge that it has. Then you connect the atoms using single bonds. Each of those will cost you 2 electrons. So you then subtract all the electrons you used for your single bonds from the total that you had in your sum of your valence electrons. And if you still have electrons remaining, you complete the octet on the atoms that are on the outside, the exterior of the molecule. Now, you have to keep in mind, if it's hydrogen, beryllium, or boron, they're not going to have 8 electrons. Okay, so we just have to adjust to that. Hydrogen's got 2, beryllium has 4, boron has 6. Everything else has got 8. If you still have electrons remaining, then you put those on the center atom. And then those will be what's called lone pair electrons. We'll be talking about that in just a bit. Then step 5, make sure everything that should have an octet does have an octet, does have 8 electrons. And if they don't, we can fix that by making multiple bonds. We haven't seen an example of that yet, but we will. And then if it's a polyatomic ion, you put brackets around the structure and you indicate the charge. Now I realize everything we're talking about here I'm not going to see this on a multiple choice exam, but you should still be writing this stuff out when you're trying to figure out the answer. Okay? So now let's jump into an example. I think what we did right before we left last time was carbon tetrachloride. And that is what this is over here. So there's no reason to do it. But on the other hand, let's look at silane, or it's silicon tetrahydride. First thing you're going to want to do is, I'll get my tab on here. First thing you want to do is figure out how many valence electrons you got. So, oops, it's not plugged in. Yikes. Okay, it's going to work. I'll have to do it with my touchpad. So anyway, we've got one silicon atom, and we have 4 hydrogens. So silicon is going to have 4 valence electrons, just like carbon does, and the hydrogens have 1. So if we do the multiplication there for both of these, we're going to get 4. So we total that up, and we've got 8 valence electrons. Now, then connect the hydrogens with a single bond. I'm just going down the list of our steps to do this. What you don't want to be doing is memorizing what molecular structures look like, because then as soon as you get the one that you've not done before, you're going to be out of luck. Okay, now we made 4 bonds, so 1, 2, 3, and 4. So each of those cost you 2 electrons. So that's going to be 2 times 4. That's going to be 8. I mean, I know this is a little redundant, but go ahead, subtract it. You can see you got none left over. So if we were following our rules, we first off figured out our valence electrons. It was not an ion, so you don't add or subtract. We connected all of our atoms using single bonds. We didn't have any electron left over, so we wouldn't do these. We didn't actually check for an octet, but the carbon did have an octet. We'll take a look at that in a moment. And it was not a polyatomic ion. So that's following your steps. So to check for silicon having an octet, it's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it does have an octet. Everybody following that? Anybody got a question? So every time we do a Lewis structure, we're just going to follow those steps. So here's some more examples. We've got ammonia. So that's going to be NH3. So we've got 1 nitrogen, and we've got 3 hydrogens. So nitrogen, if we look at the periodic table, has got 5 valence electrons, and our hydrogens still only have 1. So we multiply the number of the atom times its valence, so we got 5. And for the hydrogens, we've got 3. So altogether we have 8 electrons. So I will draw it over here. How about, I'll draw it up here. So I've got nitrogen bonded to a hydrogen, bonded to another hydrogen, bonded to one more hydrogen. And you can see that, you got 1, 2, and 3. So there's 3 bonds. Each one is going to cost us 2 electrons. So that's going to be 6. So we've got our 8 and minus 6. We've got 2 remaining. Now your next step would say, if you have any electrons left over, to complete the octets of your exterior atoms. But our exterior atoms are hydrogen. And hydrogen only wants 2 electrons. Go back here and get rid of these. So, like I was saying, hydrogen only wants 2 electrons. So looking at any one of the hydrogens, it's got 2 electrons in that bond. So it doesn't need to have additional electrons to make it an octet, because it's not supposed to have an octet. So again, don't put extra electrons on hydrogen. Okay, I'm just thinking of the various mistakes people make when they're doing these things, and that's one of them. They'll think, oh, I got electrons, I got to put them somewhere. Well, don't put them there. That's not the right place. So anyway, it's already got them. So the next thing would be, the next step would be, if you still have remaining electrons, put them on the center atom. So our center atom is the nitrogen. So now I've got a pair of electrons on that nitrogen. And those are lone pair electrons. Oops. Okay. So we've done that. We've gone through the steps to get to there. And our next step would be to check and see if everything that is supposed to have an octet has an octet. So the hydrogens are not supposed to have an octet. The nitrogens should. It's got 1, 2, 3, and 4 pairs of electrons. So that's your 8 electrons. So the nitrogen does have an octet, and that makes this over here the correct structure for ammonia, or NH3. You do need to know that where there's a bond, those are called bonding electrons, and where there is not a bond, but there's just a pair of electrons, that those are lone pair electrons. Okay, this was something a little different what we did before. Has anybody got a question? Okay, I'm going to erase and we'll do water. So, of course, formula of water, H2O, 2 hydrogens, 1 oxygen. Hydrogens, valence electron is 1. Oxygen is 6. Multiply 2 times 1, you get 2. 1 times 6, you get 6. So now we've got 8 electrons. Now we draw our structure using single bonds. And I now have 2 bonds, and each bond is going to cost me 2 electrons. So that's 4 electrons there. So I got 8, subtract the 4. I've got 4 remaining. The next step would say put those on the exterior atoms to give them an octet. But just like with ammonia, we've got hydrogens out here. They don't want more electrons, so we can't do that. The next step would say put those remaining electrons on the center atom. So I've got 4 that need to go somewhere. I'll put them on the oxygen. One more time, don't do these things from memory because you'll get one that you have no idea what it is. It is really hard to draw a dot with this thing. Okay, so anyway, we've got this structure here as our final structure for water. It's got 2 lone pairs and it's got 2 bonding pairs. Okay, anybody got a question on that? Or are you good? Okay, we got hydrogen fluoride. So we got 1 hydrogen. We have 1 fluorine. So hydrogen's got 1 valence electron. Fluorine has 7. 1 times 1 is 1. 1 times 7 is 7. Giving us a total of 8 electrons. So then I'll do it over here. I'll do a single bond between hydrogen and fluorine. That used up 2 of my electrons. I now have 6 remaining. It says then to put those on an exterior atom to complete its octet. Hydrogen doesn't want an octet, it only wants 2 electrons. So we'll put all 6 of those on the fluorine. Oh, got a pair here, and a pair here. And so that'll give us our Lewis structure for hydrogen fluoride. So is there any question on what we did here on this slide? Okay, backing up to the steps. You want to get the sum of the valence electrons. We connect everything together with single bonds. If we can, if an atom needs an octet and we still have electrons remaining, we put those on the exterior atoms. Now you want to do that in a way to where if you run out of electrons and you're not going to give everybody an octet, that you do this evenly. So you put 2 on one, 2 on another, 2 more, on one, 2 more on the other, and just, alternate around that. Don't just throw them all on one atom and leave the other one, with fewer. You want to balance that out. It'll help you get to the final structure better, or easier, I should say. And then if you still have electrons remaining, like we did on nitrogen and oxygen, you put those on that nitrogen or oxygen, the center atom. Then you want to check, make sure everybody's got an octet. And we've not seen a polyatomic ion yet, so we haven't done 6. Anyone got a question? That's our next slide, Gary, but thank you. Yeah, we are going there. Okay, so this is what we're going to be doing here. Octets, multiple bonds. And this is also a polyatomic ion. So this is a hydrogen carbonate, CHO2. So you have 1 carbon, 1 hydrogen, and 2 oxygens. So the carbon then is going to have 4 valence electrons. The hydrogens have 1, and the oxygens have 6. Now remember, when you're figuring out valence electrons, you do not include the electrons that are in the D block. You only include the electrons that are in the S and the P block. So periodic table, you don't include the D's. You just include the S and the P. And so it just depends on what is the lowest row, highest energy for that particular atom. So, if we're, if we're going, say, right here, I'm just going to make an X, then we're going to have these S electrons and these P electrons. If I'll go down here, I'll just put a Z below it, then we're going to use these S electrons and these P electrons, but not the D electrons. Okay? So the maximum you're going to have is 8 if you'll be doing this with a noble gas. I know we said noble gas make bonds, but actually we were lying to you, and you can make bonds to noble gases, but that's coming up later. Okay, so now let's finish out our math over here. 1 times 4 is 4, and 1 times 1 is 1, and then 2 times 6 is 12, and we got to do one more thing. That is, I forgot to put the charge up here on what we are trying to do. So it's got 1 negative charge. So we're going to add 1 electron for that negative charge. Remember, you add an electron for every negative charge. You take 1 away for every positive charge. So now we're going to add those up. So 4, 5, 6, 7. Okay, we got 18 electrons. Now we make an approximate starting structure. It looks like this, where everything is connected with a single bond. Now you may be wondering, well, why do I put the carbon in the middle? Well, for now, we'll go with this idea, and then later on we'll have another way of looking at it. But anyway, periodic table over here. Remember, electronegativity, highest electronegativity, upper right-hand corner. Well, you put the atom with the least electronegativity, not the greatest, but the least, in the middle. And oxygen is to the right of carbon, therefore it's more electronegative. So you're not going to put oxygen in the middle, you're going to put carbon in the middle. Now hydrogen's a little bit harder one to think about like that, but hydrogen's electronegativity is about the same as carbon. Okay, get rid of this arrow down here that I just put in. Now we've done 3 bonds, so that's 6 electrons. So let's subtract, get a marker. Let's subtract 6 electrons. And so now I've got 12 remaining. So I had 18 to start. I used up 6 to make bonds. I've got 12 remaining. And I start putting those on the exterior atoms. So I'll put a pair on this oxygen. I'll put a pair on the other oxygen. I'll put another pair on this oxygen, Oops, that one was a little messy. Put another pair on this oxygen. And I'm just going to put these up here because I drew this too close to the name. I'm sorry. And then I put another pair here. And I've used up all 12. And that gets me through the third step. So I got the valence electrons, made the bonds, counted for those bonds. That was 6 electrons, got 12 left, put them on the exterior atoms. Can't put any on hydrogen because it does not want an octet. It only wants a pair of electrons. Now my next step is to check for an octet. So I'll change colors here. I'm going to go to red. Oxygen here has got a pair, another pair, another pair, and another pair. So it's got 4 pairs. So 4 times 2 is 8 electrons. So oxygen is taken care of. However, carbon is not. And I think I'm just going to have to draw it real quick over here. So it's easier to see. Sorry, it takes a second to do this part. Oh, come on. And so now if I go looking for an octet on carbon, it's going to be those. So I've got 3 bonds times 2. It's going to just give me 6 electrons, not 8. So we don't have 8, so we got a problem. Everybody see that? Anybody got a question as to why we have to do something for the carbon? Okay, then. I'm going to get rid of this circle. And here's what we're going to do. We're going to take a pair of electrons on one of these 2 oxygens. So we could do it here, or we could do it here. And to match my picture that we're looking at, I'm going to take this pair of electrons, and I'm just going to move it from being a lone pair to being in a double bond. Did you guys follow that? I took a pair of electrons that were on this oxygen here. I moved those into the bond. And so after I do that, I now have this structure above. The carbon now has 8 electrons. If I look through here, I've got 1, 2, 3, 4 bonds. Each bond is 2 electrons, so 4 times 2 is 8. I've got an octet on the carbon. And you may be wondering, well, didn't that mess up the oxygen? No. Get this out of the way so it's not a distraction. And if I now look at the oxygen, it's got 1 pair, second pair, and then it's got 2 bonds. So 1, 2, 3, 4. 4 times 2 is 8. So the oxygen still has octet. Now let me clean all this junk up. Okay, so now we have an octet on the carbon and on the, a marker. We have an octet on the carbon We still have an octet on the oxygen. We didn't do anything to the oxygen up here, and hydrogen does not need an octet. So now we've got octets on everybody. And then clearing that out. The thing that is easily forgotten is that we need to have brackets. So we've got to put this bracket in and the other bracket, and we include its charge. Remember, we started out with CHO2, hydrogen carbonate, that has one negative charge. And so we need to show that negative charge when we do the Lewis structure. Anybody got a question? Okay, let's go over to the next slide. A little bit more of this stuff. So here's another example of the same sort of thing. We've got a polyatomic ion, NO, and it's got one positive charge. So one nitrogen, one oxygen. Nitrogen has 5 valence electrons, oxygen has 6, but it's also got a positive charge. So we're going to want to take away 1 electron. I'm just going to put a minus here. And so we're going to end up with 10 valence electrons. So to start drawing this, I've got an N and an O with a bond between. So 10 minus 2 is going to give me 8. And this is going to illustrate now why we want to alternate putting our pairs of electrons on our atoms, because otherwise we could end up with too many electrons on one of the atoms. So one pair, if there is a charge, will it be, oh yeah, will it be shown? Yeah. Okay, well, okay. Yes, you guys are supposed to remember your polyatomic ions, but probably the question will actually have the formula of the polyatomic ion. Okay, I'm not gonna put 2 different ideas together in the same question, like draw the Lewis structure for hydrogen carbonate, and then you just got words. You don't know what the formula is. So, I mean, you're supposed to know the formula, but I think that it would be more appropriate to have a question that's like, what is the formula of hydrogen carbonate? And then what is the formula for CHO2 negative? Okay. So anyway, we put in 1 pair on the nitrogen, we'll put 1 pair on the oxygen, we'll put in 1 more pair on this nitrogen, and we'll put in 1 more pair on the other oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. I am out of electrons, but yet neither atom has an octet. The nitrogen only has 6 electrons. The oxygen only has 6 electrons. You guys see that, or do I need to draw it in for you? So how you got 6 on each? I think I did that enough times. You guys probably have that. So then what we're doing when we come up to here is we take a pair of electrons that is on the oxygen, move it into the middle here, and now you've got a double bond. But you still do not have an octet on the oxygen. The nitrogen does have an octet. The nitrogen does have 8 electrons. You got 2 lone pairs and you have a double bond. So, or 2 bonds. So 2 bonds, 2 lone pairs, that's 4. 4 times 2 is 8. Now on the other side where the oxygen is, I've got 1 lone pair and then a double bond or 2 bonds. So that's like 3, that's like 6. So the oxygen does not have an octet yet. So to fix that, we're going to take a pair of electrons on the atom that does have an octet. So you want to notice that you take the side that has an octet and you take one of your lone pairs and make another bond in the middle. So we're taking, get this out of the way so it's not distracting anybody. We're going to take that pair of electrons on the atom that does have an octet and increase the bond order in that bond in the middle. We're going to move it from a double to a triple bond. So that when we're done now, we've got this. Then we need to check and make sure that each of these has an octet. Well, whether we're looking at nitrogen or oxygen, we have 1 lone pair and we have 3 bonding pairs. In that triple bond in the middle. So altogether we have 4 pairs, whether we're looking at nitrogen or we're looking at oxygen. And then 4 times 2 is 8. So each of those now have an octet. And then again, remember to put the brackets on there like we got, and remember to put the charge on there. And the charge again came from the formula that would look like this. Anyone have a question? Okay, let's move on some then. Okay, here's a couple more examples. Carbon monoxide, carbon dioxide. If we go through the steps, these are going to work out just like it did for the previous 2 examples, except these are not polyatomic ions. We're not having to put them in brackets, not having to indicate a charge. These are molecules, but it still is going to work out the same way. You get the valence electrons, you make the bonds, you put the remaining electrons on the exterior atoms, you then check for octets, you find that they don't have an octet, you take a pair of electrons, increase your bond order from single to double and from double to triple if needed, until you finally get a situation where you have an octet on each of your atoms that is supposed to have an octet. And oxygen, see, carbon and oxygen should both have an octet. I don't really feel like I should necessarily, bore you guys with drawing these out, so I'm going to leave that unless you have a question. Okay, looks like no question there, so let's go a little bit further. Now this is sort of an interesting molecule here. We had NO previously that was NO plus, but this is simply nitrous oxide, NO. So 1 nitrogen, 1 oxygen, 5 6, 11 total. Now we immediately see that we've got a problem here because there's no way we're going to have a pair of electrons for everything when we have an odd number. So things are going to be challenging. Anyway, let's go through the steps. So we got a bond between nitrogen and oxygen, takes away 2, leaves us with 9 electrons. So I'm just going to add these alternating between the 2 atoms. So pair on the nitrogen, pair on the oxygen. Now, if I were to follow what I started doing, I would have put a pair. Oh, wait a minute, I'm still not to that point yet. Okay, I'll go here. Pair on the nitrogen, pair on the oxygen. So I have used up 8 of my electrons. I've got 1 electron left to go. It's the final rose, guys. Who do we give it to? Oh, never mind, wrong show. We could put it on nitrogen or we could put it on oxygen. And for now, I'm just going to say, we're going to put it on nitrogen. You're going to see later on why we would do that, okay? So let's put it on nitrogen. Now, again, nobody has an octet. The oxygen has 2 bonding pairs. Excuse me, not 2 bonding pairs, 2 lone pairs, excuse me. Has 2 lone pairs and 1 bonding pair. So that's a total of 3 pairs. 3 times 2 is going to be 6. So oxygen is not going to have an octet, and it needs one. And nitrogen is going to be even worse off. It's only going to have 5 electrons. Or excuse me, it's not. 5 is not correct. It's going to have. It's going to have 7 electrons. Okay, it's got more. I'm sorry, did it the wrong way. So the nitrogen's got 7. So we're right here. Nitrogen has 7. Oxygen's got 6. We need to fix this. So we could take a pair of electrons from the nitrogen, put it in the middle, and it would now look like what we have over here. Okay, and that's as good as we're going to get. When we did that, now the oxygen has 8 electrons, 2 from bonds, 2 from lone pairs. The nitrogen's only going to have 7 electrons, 1 pair from a bond, and then 1 from a lone pair and 1 from a single electron. That's as good as we're going to be able to do with this. Now, of course, the question is, how do I know that the single electron goes on the nitrogen or it goes on the oxygen? And we're going to be talking about something a little bit later that will clarify how to figure that out. Okay? So, let's see here. Let me get something going here. I want to see what slides we have remaining. Okay. Okay, let's keep going. And before we do, I want to go back, though, to where it's all started from, and that was here. Oops, not there. Here. For all of these, we're just following these rules, okay? You know, we're getting the sum of the valence electrons, and then if there's an anion or a cation, adding or subtracting. We're making our bonds between them. We're using up 2 electrons, taking that out of the total, still have electrons left over, we try to make octets on the exterior atoms. If we still have remaining electrons, they go on the center atom and they'll become lone pairs. And then you go checking for octets, and then if you don't have an octet, you can make an octet by making multiple bonds. And then if you have a polyatomic ion, you got to do this stuff, brackets and charge. Okay? So now let's go to our next slide. And that is, what's going to happen if we have less than an octet? Okay, what are we going to do if we have less than an octet? We still follow the same rules. The rules don't change. We still have those. So in this case, I've got 1 beryllium and 2 hydrogens. I mean, I didn't do the formula. I suppose I should have. So it's going to be BeH2. Okay, so the beryllium, it's going to have 2 valence electrons. The hydrogens are going to have 1. 1 times 2 is going to make 2, and then the same thing here. And so we have 4 valence electrons. So you can see as soon as you draw this structure, you don't have any more electrons. You couldn't, the hydrogens don't have any lone pair electrons that you could move into the middle or anything like that. So that sort of saves you from making that mistake. But the main thing is to remember that beryllium is an exception. Beryllium should only have excuse me, 4 electrons. It does not have an octet. Now let's look at our boron trifluoride. So we got BF3. Now this is one that people mess up on sometimes. So let's try to do this and not mess up, okay? We got 1 boron, and I'm seeing people bouncing in and out of the collaborate. I hope you guys aren't having connection problems. We got 3 fluorines. So boron then is going to have 3 valence electrons. Fluorine's going to have 7. We got 1 boron, so that'll be 3. We have 3 fluorines, so that's going to be 21. So altogether, it's going to be 24. So according to what we were told in our steps, we connect everything together. With single bonds. And so that's 1, 2, 3, 4, 5, 6 electrons. So I subtract that from the total, and I've got 18 electrons remaining. And I put those on my exterior atoms. Now be sure that you do that. You put them on the exterior atoms. One more time, I'm going to say, don't just memorize these, because you're going to hit something that you've not seen before, or it's just not going to work. So we're going to stick to those steps. But anyway, let's put the remaining 18 electrons on our exterior atoms, doing 1 atom at a time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I've used them all up. They're all gone. So I have no electrons left to put on the boron. And then we could, have a question like, okay, does boron have an octet? Well, no, but it's not supposed to have an octet. Boron is only supposed to have 6 electrons within the molecule. Okay, it's only supposed to have 6, and it only has 6. So it's good. You're done. This one's over. Okay? So we don't want to do anything weird like taking a lone pair on fluorine and making a double bond between boron and fluorine. That's not right, because boron is not supposed to have, it's only supposed to have 6. Okay? So how do I know if it needs an octet? Sorry, hey, no, don't say sorry. You just have to go back to this slide. I know right now this is all new stuff, and so you got to remember some of this. Hydrogen's always going to have 2. Beryllium's always going to have 4. Boron's always going to have 6, and everything else is going to have 8. So you only got 3 exceptions here you have to worry about. Everything has 8 except hydrogen, beryllium, and boron. So that's how you do it. How about lithium and helium? What do you think? That's a good one. Helium is going to have 2 valence electrons, and I don't think you can make a compound with helium, but I could be wrong. Let's look at that a second. Well, you can't make, I know you can't do diatomic helium. I'll go back to, I don't believe we can make a compound with helium. We'll go with that. HEH. Interesting, but I don't think you can do it. Although all these weird ones, if we dig around in the research, we'll probably find that somebody has managed to do it. And I'll say I don't know the answer to that. But you certainly are not going to have to deal with helium in a compound. And your other one was lithium. So, yeah, I see what you're saying. Again, lithium's not going to be in a covalent compound. Lithium is going to be in an ionic compound. It's going to be more like, lithium chloride. Something like this. So it's ionic. Going to be Li plus and Cl minus. So that's not, so we don't have to worry about it being in a covalent compound. I mean, beryllium is actually sort of weird because it should just be a metal and not be involved in a covalent compound, but it's possible to have the beryllium hydride like we saw. Okay. Oh, there I go. Well, they are and they're not. I mean, you will see people say, okay, there's Lewis structures for ionic, and but then their Lewis structures just look like Li plus and Cl minus, and they'll do something like they'll all the dots around the chloride, so that the chlorine in the chloride will have 8 electrons, 8 valence. And the lithium will have none. That's, I don't know. It doesn't do it. Doing Lewis structures for ionic compounds doesn't really help us. So I don't really do it. I usually don't ever even talk about it. But they are really important for covalent compounds. Everything is, in covalent compounds, everything is based on these Lewis structures. Okay, we've got one more oddity that we need to get to, and that is what's called expanded valence. We just did this, less than an octet. Our next slide is expanded valence. And you can see that those middle atoms have more than an octet. We got 10 over here, and we got 12 over here. So these are only going to be for atoms that are big enough that we can have that many electrons around the atom that we have enough space. And so here's how you would look at that. Okay, I really wish I had a periodic table right here. Yeah, need one. Anything that's, hang on a second here, let me do this, because you guys really do need to see the periodic table for this. And what I'm going to do is I'm going to share my screen with you guys. I think that, okay, so I'm going to stop the presentation here and go to sharing my screen, because I think you should see this periodic table. Okay. So, whoops, I was trying to draw on it. It won't let me draw on it. Anyway, chlorine, sulfur, phosphorus, those can all have expanded valence. And so can the atoms below that, like bromine and selenium and iodine. They can do it too. Fluorine is too small. Oxygen is too small. Nitrogen is too small. So, mental note, phosphorus, sulfur, and chlorine, and everything below. I think what I'm going to do is also draw that on the slide that we were on. So I'll put that slide back up. Okay, so we were here, and let's do this. Phosphorus, sulfur, chlorine, and argon. And then selenium, bromine, krypton, and then iodine and xenon. These are the ones that can have expanded valence because they're larger. Okay, everybody got that? Take the row where you see phosphorus. Phosphorus, sulfur, chlorine, argon. These are going to include noble gases. Then look right below that, and you have selenium, bromine, and krypton. Look below that, you've got iodine and xenon. Okay? So now let's see how this actually would work. I'm going to erase that. I'm going to just look at this compound I have on the left. So you've got phosphorus, you've got chlorines, and you've got 5 of them. So PCl5. So I have 1 phosphorus, and I have 5 chlorines. So phosphorus has 5 valence electrons. Chlorines have 7. So we're going to get a total. 1 times 5 is 5. And 5 times 7 is 35. So I've got 40 electrons. I put the phosphorus in the middle, connected the chlorines. And at this point, I've made 5 bonds, right? So I've got 5 bonds. So 5 times 2 is going to consume 10 electrons. So if I start with 40, subtract the 10, I've got 30 remaining. Oh, somebody just drew a circle. It wasn't me. Okay. And I can't, oh yeah, I can. Okay, it's gone. Anyway, so now we've got 30 electrons remaining. I've got 5 atoms. So that means I'm going to be able to put 6 electrons on each of those atoms. Or I could just do it like we've been doing it. No, I'm not going to do it. That will take a long time to put all these dots on there. But anyway, I've got 30 remaining valence electrons. I can divide that by 5, and I'll see that I've got 6 electrons per atom, which would then produce that structure. Okay, has anybody got a question about that? Okay, I'm not getting any question. So let's erase it. Look at the other side here a second. So on the other side here, I've got a single sulfur, and I've got 6 fluorines. So I've got 1 sulfur, 6 fluorines. Sulfur has 6 valence electrons. Fluorine has 7. So that's 48 altogether, I think. I left out my step of drawing all that out, but I think I've got that right. Yeah, 42 plus 6, yeah, 48. So we're going to do the same thing we did before. We're going to put the fluorines around the sulfur. and we're going to use up 6 bonds or 12 electrons. Okay, so we used up 12 electrons, making those 6 bonds, and I now have 36 electrons remaining. I have 6 fluorines, so if I take the 36 and divide it by 6, I get 6. Hey, so I can put 6 electrons on each of those fluorines. Now, on going back to octets and all that stuff, I'm going to erase. The chlorines all have octets, 3 lone pairs and 1 bonding pair, so 4 pairs altogether, so that's 8. Same thing's going to happen with the fluorines. They're all going to have an octet, but again, the phosphorus is going to have 10 electrons, and the sulfur is going to have 12. But it's okay because they're big atoms and you can put a bunch of electrons around it. Okay, anybody got a question? While you're thinking, I need to look at what we're doing right now. Okay. So what I want us to do at this point now is we're going to start working on a worksheet, and I'll need to show you where that worksheet is located, and then in the worksheet you're going to do Lewis structures in groups. Okay, so let's do this. I'm gonna stop our presentation right here, and I'm going to share my screen, and I'll show you where you can find that. Okay, so looking over here, and this is actually not going to be in the worksheets, okay? At least I don't think it is. Let me make sure that's true. Don't think so. Oh, no, it is there. Okay. Yeah, couldn't remember if I moved it over or not. So what you're going to be wanting to look for, again, is, let me just go back, because I did that kind of quick. So you're going to get into course materials, and you're going to click on worksheets, and then you're going to scroll down till you get to chemical bonding and moleculometry. You click on that, and it says molecular geometry lab. We used to work on this in, when we were having our lab period, which we will be able to do. Well, not this Wednesday, so maybe not. But anyway, we will be working on it in class and probably in the following Wednesday. So anyway, clicking on it, molecular geometry lab, you're going to get this worksheet. So it's going to have a molecular formula, such as this one for carbon monoxide. And you got a space here where you would put in the valence electrons. And sorry, I should have asked you guys to print this out in advance. but you can probably just write this out on some note paper. But anyway, put in the, first thing you're going to do is put in the total number of valence electrons. And then you're going to want to do the Lewis dot structure. Now the rest of these columns, we're going to come back and we're going to pick those up a little bit later. So electron geometry and all that to the right, we're not going to do that today. We're going to just worry about getting our Lewis dot structures. So what you're going to be doing is total valence electrons, Lewis dot structures for carbon monoxide, boron trichloride, sulfur trioxide, that's methane, CH4, phosphorus trihydride, dihydrogen sulfide, phosphorus pentachloride, sulfur hexafluoride, boron trifluoride, xenon difluoride, sulfur hexafluoride, iodine pentafluoride, xenon tetrafluoride, and then we got some polyatomic ions. This one is sort of like the one we did on the slide, but it does not have a hydrogen, and it's got one additional oxygen. And the charge is different. So it's not the same, but you do it the same way. Then we have nitrate, and then we've got a few more here, oxygen difluoride, sulfur dichloride, and then we've got C2H4 and C2H2. So anyway, I want you guys to, in your groups, figure out what the Lewis dot structures are. And what I would suggest you do on this is that you bring up the whiteboard in your group. So that's one of your options. You try drawing it out, and when you think you have it, do a screenshot of it so you've got a record of it. Okay, I'm not taking these up. This is not going to go like that. But you should do that, because then after you guys have had opportunity to work on this, I'm going to ask you for your answers, and we'll go to the groups, and you'll have an opportunity to share what your structures were. Okay? So let's go back to here. And I'm going to stop sharing my screen. Has anybody got a question on what I'm asking you to do? Okay. Got a group. That's interesting. It looks like everybody was in groups and it dumped you out of your group. Oh, that's not good. Okay, well, I'll have to do that again. Sorry, guys, it'll take a second for me to put you all in your groups.